So today we're going to explore the variance. I get a lot of questions from my students about the variance of a sample, why we divide by n minus 1 instead of just n. I mean, yeah, if we compare this to the population and mean relationship, both just have to be divided by the number of observations, right? To get the population mean, the sum of values divided by the population size, big N, while the sample mean, the sum of values divided by the sample size, small n. But why aren't we doing this for the variance? Disclaimer, this video is not a proof. The proof is quite lengthy in mathematical statistics, so we'll just be verifying this with an example. You see in the screen in front of you the formula for the population variance and its unbiased estimator, the sample variance S squared. Take note that if we want to better estimate sigma square, the population variance, we use the sample standard deviation as its point estimate. And that means we're going to divide by its degrees of freedom, which is one less than our sample size. And let's verify this that dividing by n minus 1 is better than dividing by n. So let's assume a small population as shown here 30, 25, 25, and 30. Um, let's give the true population variance. And to do this one, we need to get first the mean mu. To get the mean mu, we add all of the numbers 30 plus 25 plus 25 plus 35 and a 40. The sum here is 155. And we have to divide this by the population size of 5. So 155 divided by 5 is 31. And that means to get the variance, the symbol is sigma square. We subtract our original values, each of them, by our mean. So 30 minus 31, that's a negative 1, and then multiply the result by itself. So 1 times 1 is a 1. The first number here is 1. Next, the second, and the third number are the same. So that means I get the same results. 25 minus a 31 is a 6, negative 6 to be exact. Negative 6 times negative 6 is a 36. And that means the third number is also 36 because they're the same, 25. So let's go to the fourth. 35 minus a 31 is a 4. 4 times 4 is 16. And the last is 40. 40 minus the 31 is 9. 9 times 9 is 81. And the sum of these values is 170 divided by, again, 5 population size. So 170 divided by 5 is 34. This is what we need. But if we're just interested in getting the standard deviation sigma, um, whatever our variance is, we just get its square root, which is roughly equivalent to 5.83. Yeah. Although we're not concerned with the standard deviation as of the moment because we're concerned with the variance. So this is our target parameter. This is our target. So using our population, what if we take a smaller sample out of it? So let's just use the first four values 30, 25, 25, and 35. And before we start, let's first write our target parameter a while ago. We identified this one as 34, right? So let's now calculate first the mean of the sample. And the symbol is x bar because we have a sample mean. So 30 plus 25 plus 25 plus 35. The answer here is 115. Then divide by 4 because we have 4 values. And 115 divided by 4 is 28.75. Oh, decimal. That means I'm going to expect decimal values for when we proceed to the next step. You know, the subtracting from the mean and then multiplying by itself portion. And let's do that. So 30 minus the mean 28.75, that's 1.25 when you subtract, then multiply by itself 1.25 times 1.25. is 1.5625. Second one, again, and the third are the same. So that means I get the same values. So 25 minus 28.75 is a negative 3.75. And when you multiply it by itself, that's 14.0625. And that means the third is also the same, 14.0625. Last is 35. 35 minus 28.75. That's a 6.25. Then multiply by itself. The result is 39.0625. And when we add all these numbers up, the result is 68.75. There we go. This is what we need. And let's now proceed to case 1. When we divide it by n, which is 4. So what happens if we divide 68.75 by 4? The result here on the calcu is exactly 17.1875. How much error does this estimate have over the variance? So error is the difference between your estimate, in this case 1875, and our parameter, which is 34. And the difference here is 16.8125 negative. This means that we are short by 16. Our estimate is short by 16. How about the second one? Case 2. What if we divide by, this time, the degrees of freedom, which is 4 minus 1. We divide by 3. So that means 68.75 divided by 3. The result is 22.92. And how much error did this incur? Um, Error is the difference between our estimate and our true parameter. And the difference here is also negative 11.08. This means that yes, we are also short. However, we are just short by a much smaller amount, by 11 points, you can say. When you divide by 4, when you divide by 4, we are short by 16. But when we divide by its degree of freedom, 3, we subtract from 1, 4 minus 1 is 3. Our short amount was smaller compared to our target parameter. So, yeah, I guess this is a good example why dividing by degrees of freedom provides a much better estimate than when we divide by n. We have a much lower shortage of the amount compared to when we divide by n. Uh, this, I think, is a good example um, to show that dividing by n minus 1 really is better than by dividing by n. And that means, since we're talking about degrees of freedom, this leads us to the question, what the hell is a degree of freedom? And if you just do a quick Google about this, a degree of freedom represents how much freedom a set of data has to vary when estimating a population parameter. So in our case, write the formula for s squared, the sum of x minus the mean squared divided by n minus 1. Recall that n minus 1 represents the degrees of freedom. And this formula, let me use black. This formula estimates our sigma. And in this formula, we are fixed into having an x bar. So that means, let's just have a hypothetical example here. What if I have 4 numbers here and I need strictly an x bar of 24? On the first blank, Can I choose any number that I want? The answer is yes. I can choose any number here. For example, I can write 21. I am free to choose whatever number I want here. How about on the second blank? Am I also free to write any number here? And yeah, for example, I can write here 23. How about on the third number? Again, I am also free in writing any number that I want here. In this case, I can write 20. But what about the fourth one? I need an x bar of 24. Can I choose any number that I want? And the answer here is no. I am no longer free to choose any number that I want. Because if I need to get an x bar or a sample mean of 24, I strictly need to get a 32 so that I can get a sample mean of 24. And I am no longer free to choose any number that I want. I am forced to write 32 as my last number. So out of the four numbers here, I can just freely choose 4 minus 1 or simply three of them so that I can get an x bar that I need so that I can effectively estimate my sigma square. So this means degrees of freedom is how much freedom we have in our data that is free to vary. So that's it. Why is it better to divide by n minus 1 or the so called degrees of freedom? We were also able to explain what degrees of freedom means. And this concludes our video. See you in the next and have a friendly day.